Okay, so what we have here is somebody throwing a ball at an angle. So if this is the horizontal direction, the ball is being thrown at this angle. And we know all about this because of everything we did with vectors last chapter. So as the ball is moving through the air, it'll change its position. And the change in position will happen both horizontally and vertically. Okay? So for example, if the ball starts out here, at the end of a certain number of seconds, horizontally, it would have moved from this position to this position. Vertically, it's the same. It starts here, it goes up, and then it'll eventually come back down all the way to the ground. What we can do is we can graph these distances independently of one another. So in this case, we've graphed just the vertical distance with respect to time. And notice we did change the equation. Okay, we just swapped these because it was wrong before. So if you look at just the graph for the vertical distance, at time t equals 0, the ball was at a level of 40 feet above the ground. At t equals 2 seconds, so 2 seconds later, the ball is now at about 79 or so feet above the ground. At time almost 4 seconds, the ball is now on the ground. So it was here, it moved up, further down, down, and then finally hit the ground. If we graph the horizontal distance, at t equals 0, it was at 0 meters. Then it started moving away from the player. At t equals 1 second, it's about 50 feet away from the, or 50 meters rather, away from the player. At t equals 3 seconds, it's about 120 meters away from the player. So it just keeps moving away from the player. So this is one picture of the scenario. This is another portion of the scenario. Each of these have their corresponding equation. If you notice, this is a quadratic equation because this is a parabola. A is negative, and it should be because the parabola is facing down. This is a linear equation. So, instead of having, for example, x is equal to 5t, the constant now is 30 radical 2. But it's a linear equation. All right, so like I said, each of these graphs only gives us part of the picture. All right? So what you want to do sometimes is you want to morph these two into one graph so that just by looking at one graph, you can get the entire story, not just part of the story. Okay? That's what we're going to do. That's what parametric equations is all about. All right? It's combining portions of the equations so that together you get the full story behind what's going on.
Wouldn't the first graph also include the normal line, considering it's going right? That's his job, like vertically and.
Well, this does not tell you what the horizontal distance is. This only tells you the vertical distance. Okay? This only tells you how high up it went and how far down it went. But it doesn't tell you horizontally how far the ball got away from the player. Okay? All right, so what we're going to do here is we're going to create a chart of values relating vertical and horizontal distance. So let's see, when t is equal to 0, what is the horizontal distance? We're going to get these values and plug them into the horizontal equation. So when t is equal to 0, x is equal to how big? 0. When when t is equal to 1, this is 30 radical 2, and it's exactly how much?
30 rad 2. Oh, you want
which is?
Oh, sorry.
42.
Okay, so it's about 42. When?
Do you not want the in rad form?
No, we want it in a form precise enough that we can graph. All right, when t equals 2, we plug 2 into the equation for x, and we get 85.
Say what?
60.
It should be 60.
Dude.
How is that 85?
Is that 85?
Because 2 times 2 is 4, which this.
Right, so it'll be x is equal to 30 times radical 2 times 2. So that's 60 radical 2, which is about 85.
Okay, where did you get this sec? But is
Okay, so you multiply the coefficients
Wait,
outside.
is
t in the radical or?
No, it's
Oh.
30 radical 2 times t.
We should put a little dot.
Right, remember we said it was a linear equation. If t is inside the square root, then it will not be a linear equation.
9.
When t is equal to 3, it's 127. Now, similarly, we're now going to plug the same values for t into the equation for y. So when t is equal to 0, y is equal to 40.
Wait. So t is then multiplied again by what's it called? By the 30. So you multiply t times 30 and then times root 2.
Right. When t equals 2, the y value is 61. When
t equals 1.
When t equals 1, it's 66. When t equals 2, it's 61. And when t equals 3, the y value is 23. Now, what I want to do is I would like to graph x versus y. So in this graph, it's no longer t versus distance. It's now x, the horizontal distance, versus y, the vertical distance. Okay, so if you look here, when x is 0, y is 40. When x is 0, y is 40. Now, at what point does this happen? When t equals 0. So you attach that as a label. Okay, so here's a way that you can incorporate 1, 2, 3 pieces of information onto one graph. All right, so let's do another point. When x is 42, y equals 66. That's this point. When x is 42, y equals 66. At what point does this happen? When t is equal to 1. You tack that on as a label. All right? And you continue this way. The next point is x equals 85 and y equals 61 at t equals 2. And the last point is at t equals 3, y equals 23 when x equals 27. All right? So this picture now does tell us the entire story. It tells us how time is related and how x and y are related to each other. Now, you can also combine the equations into one equation just containing x and y. Remember, here are the equations that we started with. So x is equal to 30 radical 2t. Y is equal to this quadratic equation. I want to transform this into an equation that just says y equals a function of x. So how do I do that? We're going to do an example right now. I solved this for t, plug it in here, and magically I get one equation. So you morph 2 into 1. Okay, we're going to do a concrete example right now. All right. What we talked about, combining the two scenarios, the horizontal distance and the vertical distance, into one, is the concept behind using parametric equations. The parameter is the variable t. Okay, this is the one that then is eliminated when we write an equation in just x and y. Okay, the orientation is the direction over which the curve is traced out. In this case, the orientation would be represented by arrows that literally show you the direction that the curve is being traced out. It might be very obvious here, but in some cases, when our equation is circular or it's got different shapes, it's probably useful to know exactly what orientation it has. Okay. Let's do this example. It says sketch the curve given by the pair of parametric equations over the given interval. I have an equation for x, an equation for y, and I'm given values for t. Okay? Yes.
If it gives us -3 to 3, how come our graph only gives us -3?
Oh, that's fine. This is t.
I know.
All right. So you'll see what happens right now.
The X and
All right. The x and y will be different. So this is -3, -2, -1, 0, 1, 2, 3. Okay? We're going to plug each of these values in our equation for x, then into our equation for y. Let's do the equation for x first. When t equals -3, x will be -3 squared minus 1, which is 8. When t equals -2, x is going to be 3. When t equals 1, x is 0. When t is 0, x is -1. When t is 1, x is 0. T is 2, x is -3. And finally, we have +3 and +8. Okay? This is a sideways parabola, remember, so it's going to be symmetric. All right, what about for y?
1 and 1, 4 for -3. 1, 2, 5.
So when x is equal to -3, it's going to be -3 over 4 plus 2, which is 1.75. Here we have -0.5 plus 2, 1.5.
No, isn't it
1.25?
like 1.25?
1.25.
Yeah, 1.75, so.
And this is 1.75. When x is 0, we get 2. When x is 1, what do we get?
2 and 1, 4.
2.25. When x is 2, 2.5. And finally, 2.75. Now, we're going to transfer this onto our graph. The axes here are x versus y, so we're going to graph x versus y, right? Not t. All right, so when x is equal to 8, y is equal to 1.25 here. At what point does this happen? When t is equal to -3. Okay? So now I have all this information in that one point. When x is 3, y equals 1.5. This happens at t equals -2. When x is 0, y is 1.75. When x is -1, y equals 2. This is at t equals 0. When x is 0, y equals 2.25. It does come back. My points are disappearing. When x is 3, y equals 2.5. This is at t equals 2. And when x is 8, y equals 2.75. My points disappeared.
Oh, so it's like a parabola, basically.
Right.
Right. It's a parabola.
Okay. And here is t equals 3. And the orientation of this is this way. Obviously, since you've got your points per time on there, it's sort of obvious, but the arrows would represent the orientation.